it's just.
There you go. You will see it. I will send you an email later. So it's open.
So you're directly collaborating with NVIDIA?
Well, we have a small academic grant. So you basically write a, I think, 3,000 word proposal, what you're trying to do, and then they just give you all the hardware you want.
That's great.
It would be interesting to.
Yeah.
Well, I've given a couple of these talks, and everybody's most interested about the NVIDIA thing. I'm more than happy to give you some names there and how we should write. But it's NVIDIA, but they're not public relations. So
Yeah, sure, I understand.
You don't have to write a good proposal.
Like how many GPUs can you get?
We got 4 by now. In principle, you get 1 per year and researcher on the proposal. And ultimately, the first proposal we just asked for 1, and then they said, "Oh, we don't have this one, and we want something else." And then we said, "Yeah, that's fine. By the way, can we have 2?" And he said, "Yes."
Okay.
And we have another proposal.
So usually,
5 more minutes, yeah.
In Oxford, we call it Oxford time, which is the time plus 8.
plus 8.
Sounds good.
Ciao.
For this these numbers, it's no structure.
Very nice.
Show you how it works out. To be as reliable as possible. So now the project basically went back to just being a simple comparison, let's say regression.
Yeah.
With him, I mean, my general project is more ambitious, but will probably not be carried out.
Yeah.
That's what it's expected.
It's a European way. Yeah. If you can justify what you're doing, you can do a lot of things differently than you think they will work.
Yeah, you cannot really know in advance what is going to happen. It is a molecular cloud thing. You're basically trying to infer the turbulence index.
Yeah.
So it's just a regular regression.
No, there's no need for deep learning if it's not necessary. Shooting.
I mean, like we're using still a neural net to do that. Yeah. But no GANs and no sophisticated stuff.
Yeah.
For now. Let's see.
Well, we should probably give me a ride,
yeah, I could give you a ride to the station.
give me a ride, then we'll talk. So 4:45.
Adesso dobbiamo premere il bottone arancione. Dobbiamo passare per lo studio dicendo o parte in automatico. Sì, l'ho filmato, ha fatto posso andare? Ah, vabbè, grazie, perché non so come funziona.
Se vuoi, sì, se vuoi, non so, già scritto.
Scrivendo poi così scrivere
I'm not sure if I need one. Because I don't.
This is yours?
Yeah.
Oh, okay. So.
No, don't worry about it.
No. Since streaming, maybe it's better to use the mouse pointer. So I also stream. Okay, unless I mean. Well.
Yeah.
Then I guess we can start. Okay, so let's start. And the speaker today is Julian Merten. He's currently an Astrofit fellow in Bologna, and he's going to talk about cosmology and machine learning. And I hope, I know that this is potentially a very interesting topic that I hope will bring about collaborations, and please do ask questions because it's a very hot topic and he's a very smart guy. So I'll leave the floor to him.
Thanks, Maya, for the interesting introduction. You all can hear me all right? Yeah. So again, this is a talk about machine learning and yes, also deep learning. Applications in cosmology. I'm afraid the cosmology side of things will be a little bit on the downside of this talk, so I will not talk too much about the cosmological background of each of these applications and their importance and so on and so on. The aim of this talk is rather really to give you an idea what you can use machine learning for with the application of cosmology, okay? And I hope it will all make some sense in the end. And probably, as Mario said, gives you an idea of what you can do with machine learning these days. What has actually been done a lot already with machine learning these days, but in other fields, which is not even physics, but free industry, self-driving cars, media sector, and so on. It's amazing what you can do with these techniques, and I hope to give you a little bit of an idea of what you can do in a scientific context. Okay. So this is my very embarrassing slide about what machine learning is, because it's really incredibly simple. Okay. Machine learning is you have some side X, a data vector. Okay. This data vector can really be anything. It could be an image. It could be a really, for your application, it could be a CCD image. It could be a catalog. It could be an input catalog of galaxies with certain properties and so on and so on. So all in all, it's a multi-dimensional data vector, right? So it could be audio clips. It could be 3D particle distributions from a simulation. Okay, it could be anything. But we subsum all these different data vector under just the quantity X. Okay?
On the other hand of the whole thing, on the other end of the whole thing, you have y. Okay, and this I will just very generally describe as labels. Okay, with labels I mean some kind of general, probably more general property of that data vector. Okay. For example, you have a 3D particle distribution of a numerical simulation, and in cosmology, typical labels to that distribution would be the cosmological parameters. Okay, so in what cosmological setup was that simulation run? For typical images, a typical classification problem would be: oh, is that a cat, a dog, or an elephant? Okay, these are the typical examples. And machine learning is nothing else than having a machine in the middle which makes this translation. That's machine learning. Okay? And usually there are two main aspects to making this translation. In other words, converting f via a function or a machine f into the labels y. One is we want to find some general properties of our sample. Okay? We want really to define, oh, is that a cat, is that a dog, or we don't care if that's cat named, you know, Anna, or if that's the cat, or that's the dog called Paul, or whatnot. We are really interested usually in, is that a cat or is that a dog? In other words, we have some kind of compression in between, some kind of representation. We are not interested in an individual sample, we are interested in a general property in that. So any of these machines usually has some kind of representation or compression step in between. Which means you're converting that data vector into something which is usually dimensionally reduced, and then you use this dimensionally reduced object to make the actual inference step, the actual classification or regression step, which I just call here label mapping. So really just go from the sample to the labels, usually with some kind of representation step in between. And there are different kinds of machine learning depending on what kind of data you have available. If you have, for example, a large so-called training set of collections of x and y, so you have collections of data vectors with their labels already associated, so something which is supervised, so you can supervise the machine. In other words, you can train the machine, or otherwise you're basically fitting your data set. Okay? This, all what I will be presenting today will be in that category. However, there's also a thing called unsupervised learning, which in this sense, in this case, you don't have the labels a priori. Okay? So you just have your data, and you basically want to find general properties of your data from the data itself. Examples for that would be clustering algorithms. So are there, you know, groups of data vectors which cluster in some kind of space? So for example, is that globular cluster or that globular cluster after some definition that I already forgot from Mario's talk 2 days ago. Sorry about that. Other applications of that would be a thing called an autoencoder. An autoencoder is the data vector x is the same as the label. Okay? All you do is you're applying a machine to recreate the same thing. Why is that interesting? Because along the way, you may learn a lot of the representation of that object. Okay? That's also called representation learning, but also a very good example of unsupervised learning, because your input is your output. And you basically try to learn about the general structure of that object along the way. This is why this is interesting, and called representation learning for that reason. Highly interesting topic. Unfortunately, I'm not going to talk about it today. And that's machine learning. Okay. Sorry for the word AI, but it's just such a hot topic these days. Machine learning falls into the general category of artificial intelligence. I don't really know what artificial intelligence really is, but it probably is you use some kind of optimized algorithm to fulfill a task. I think that's probably it. And within that landscape, you have all kinds of subsets going basically up in their flexibility of doing a task. The very simple thing that you can do is really a rule-based system. Okay? In other words, you have some data. For example, you have an image, and you know that there's a green traffic light. There's a certain amount of green. No, actually, that's even not rule-based. You have data which tells you there is a green traffic light. The rule would be go. The other data would be, or the other sample would be, you have a red traffic light. The rule would be stop. Okay, that's rule-based. You need to basically create a dictionary, a list of rules, given very specific input leading to a task. Okay. The next step would be classic machine learning, which is something here you actually apply some kind of fixed technique to your input vector to come to this basically same conclusion. The idea here would be, instead of saying this is a green traffic light or a red traffic light, the idea would be give the algorithm a picture, I don't know, count the amount of green pixels, and given a certain threshold, go. Or if, count the amount of green pixels and red pixels, and given that result, go or stop. Okay, that would be already in a sense machine learning, because you do some manipulation of your data, you learn something from your data by just applying a fixed method. Okay, and the fixed method here is really just count pixel values in a certain color. Other operations would be take a power spectrum of that and measure the amplitude in that bin. Okay, something like that in a more cosmological context. And then you go into the realm of deep learning, where that method that you apply to your data is not defined a priori. Okay, so the method is actually so flexible that it finds its own mapping between the input to the data within certain limitations that I'm trying to explain in a minute. Okay, but that's pretty much the AI landscape that we have these days. Here again is this representation learning aspect here, which is that additional step that I just described, that you're really trying to understand the inner workings, the inner structure of some kind of data vector before you make your decision and so on, instead of just applying fixed, predefined rules, which have basically no flexibility to really adapt to the task. We will talk a little bit about this, but most of this talk we are going to be in this very flexible realm. Okay? And that brings us to the idea of deep neural networks. They have a lot of names, artificial neural networks, totally fine. Multi-layer perceptron, that's how they were originally called, MLPs. If you want to be fancy, you can call them a directed anticyclic graph. So yes, they are mathematical objects with properties and rules and proofs and whatnot. And what a deep neural network is really just the very basics of machine learning. You basically apply a long, deep chain of rather simple mathematical operations to go from an input data vector to some kind of output label. Okay? And so this is pretty much the very definition of machine learning that I gave you earlier. The important thing here is there's no clear definition of this process. But as you can see, you can cast it in the mathematical framework. The important bit here is really that you have all these little steps along the way. So you have a clearly defined graph of well-defined mathematical operations. We will make examples in a minute. And an example for this would be, let's have a data vector x, which is an image. Okay? An image of 64 by 6, an image is a two-dimensional data array of, in this case, 64 by 64 pixels. And let's say it has 3 channels, okay, 3 colors in each of these pixels. Let's perform some first operation. I will give an example of what that could be. That reduces that dimensionality in some sense, so it reduces the spatial dimensionality of the thing, but it kind of highly increased the representation dimensionality of the thing. So instead of describing that image by only 3 color channels, we are now describing it something which has a much higher dimensionality. Okay? And then we go further down, we further reduce the spatial dimensionality and leave our representation channels and so on, until we are just describing that image with just 128 numbers. Okay? We have lost all the spatial information and have just these 128 channels in the end. And for that, we use some kind of linear operations to map that into our cat dog example, for example. So this is a very, to give you a very simple example. The important thing for this, so this we do supervised learning, so we want to train something, we want to fit something. So in the end, we have training data for which we have the data vectors and we have the labels. In other words, we can compare the current performance of our deep neural network to answers that where we know the two answers, okay, to data sets where we know what label we want to expect. This means we can define a loss function, okay, we can define some kind of probability of that this is a good solution. And then we are just optimizing that loss. We are just minimizing that loss with some kind of optimizer. For this, we need gradients in order to make this optimization fast and stable and robust. And that's also the very important point why these operations along the Y have to be relatively simple, because if those are relatively simple operations, for each you can define the gradient with respect to the parameters of these operations and so on. And then the magic of Rummelhardt 96 comes into play. This is the famous backpropagation algorithm. In other words, this is a very simple network. Okay, I will show you networks in a minute which have hundreds of layers and tens of millions of parameters. Okay, but still, backpropagation algorithm works. We can keep track of all of our gradients of the loss with respect to the parameters of the network, and we can optimize the whole problem. Okay? Deep neural network, that's what it is. Why is this great? Because you can build these things enormously deep. If you ask me personally what a deep neural network is, it's a brute force way of mapping between samples and the labels. Okay? It's a brute force way of fitting. And it works because you can use millions over millions over millions of parameters to describe something. You can even totally overshoot. You can, there are easy regularization schemes in these networks and so on. You can describe an incredibly simple problem with an incredibly deep network and still get a reasonable answer. Okay? So from that point of view, it's kind of easy to apply. And in fact, if you go into the deep learning business, it will be rather easy for you to produce good results within a relatively short time scale. So, what are examples for these layers? Here's an example if you have image data. A typical example would be just a convolution. Okay, you're trying to extract certain features, certain scales from your image by moving a filter over your image and basically record the response of that, so to speak. The parameters in such a layer are just the kernel itself, okay? The weights that are sitting in each of these convolution entries. So basically, the weights that you're here moving over this image. Really just a convolution, nothing else. Another, I told you there's a lot of dimensional reduction involved. That would be pooling layers. So for example, you have that image, and in that whole gray area, you just take the maximum in that area, or you take the mean in that area, something like that. That would be a typical example of a pooling layer. And once you have only one-dimensional data vectors, you can use these so-called affine layers. Sometimes they're also called dense layers. Sometimes they're called fully connected layers. This is really just a linear mapping between a relatively large array into some kind of smaller array by some matrix with the appropriate size. So you basically, this is really just some kind of weighting operations of those different data vectors that go in to map them into something which is much smaller. And those are the typical examples for neural networks that you would apply to image data. Why does this work? To give you an idea, on top here, you have tipped, it's already a little bit older, but these are maybe 1 year ago or 2 years ago were the most successful neural networks for image classification. And the number of parameters, this number is real, okay? That last thing there has 138 million free parameters, okay? In order to just walk through the network, basically have an input image in, something like 256 by 256 pixels, and get an answer, a class out, a single number, if you want to, kind of a single number. You need, what is this? This is 15 billion operations, okay, numerical operations. And just to store these parameters, you need this amount of storage on your device, okay? If you want to do 15, and you're trying to optimize 138 million parameters with an optimizer where each function call needs 15 billion operations, okay? In other words, if you have a network that deep, and they need to be that deep to be functional in some sense, you need to have them run extremely fast. And the route to that are GPUs, these kind of operations that we are using, or linear operations, convolutions, and so on, can be parallelized extremely well on GPUs, so on many core processors. And this was the one reason why these things have really taken off in the last 10 years, incredibly well for running deep neural networks. As a matter of fact, NVIDIA, which is, makes their money with making 16-year-old boys and girls happy, they have a small academic grant program. You write them a 3,000-word proposal, and they basically give you as many GPUs as you want, because we scientists we are a good public relation for them. We are good advertisement. Okay. If you talk to NVIDIA and you know that you have a problem that you can run fast on a GPU, basically just talk to them, they will happily give you everything. In Italy, by the way, this is difficult because of the Italian customs, and it's really hard to get presents from Hong Kong. So our 4 GPUs in total that we got from NVIDIA were sitting for almost a month at Bologna airport because nobody was believing that this is a legitimate package. Thanks, Italy. Anyway, we got them, and actually for tax purposes on my boss by now, but they're a gift, okay? We have not paid anything for that. And that grant that I'm writing here is roughly worth around 15,000 euros, okay? Write them. The other thing is, the amount of time that I spent on describing this probably gives you a good idea that this is really hard to implement, okay? If you really want to sit down and implement all this, go through the papers, implement all these algorithms from scratch, and have all the right layers in place and so on, can be a real pain. And I highly advise you never ever in your life do that, okay? Because a lot of smart people have done that for you. And believe me, they have done it a lot better than you will ever be able to do it, okay? Because they're computer scientists. There are libraries which do everything that I described here for you, to some extent. Most importantly, I don't know who of you has heard about TensorFlow. TensorFlow is Google. This is what Google runs on. If you put a translation into Google, some machine somewhere in some container actually will run something on TensorFlow. There are other options. Keras is a high-level library. This is all in Python. You can all do this in C if you have to. I think there is nothing for Fortran, I'm sorry. But this is all available. All these libraries are fast. They all call CUDA libraries on the bottom. You don't have to care any about this. They are Python libraries which do that all for you. This is the other big reason why this has really taken off recently. They make it simple. Okay. Why do we care about this in cosmology? First of all, I'm a cosmologist. What I'm most excited about right now are all these weak lensing surveys, okay? DES is running, KITS is running, HSC is running, Euclid is hopefully coming sooner or later in the form that I want. WFIRST is going to come eventually. LSST is actually a real picture by now, and so on. So all these weak lensing surveys are coming. In other words, we are really starting to probe the nonlinear late-time regime of structure formation. I kind of told you I'm not going to talk too much about it. I love talking about cosmology, but this is a different. Anyways, I'm excited about nonlinear late-time evolution of the universe. Why does that matter? Because with sincere apologies to all theorists working in the area, theoretical predictions in the nonlinear regime of structure formation with baryons, which have the precision and accuracy that we need to do the forecasts and or to do the prediction or the inference on certain cosmological parameters, on properties of dark matter that we want, and so on and so on. Theoretical predictions of that form currently come from numerical simulations. Full stop. Okay? And if you accept the fact that your predictions come from numerical simulations, then classical techniques of describing that data, taking a power spectrum, taking two-point statistics, taking a radial density profile of a halo or something like that, sorry, it doesn't really cut it. This is a massive compression. I told you a certain amount of compression is good, but this is a total over-compression of data. It has obviously its roots in, okay, these are the things that we can theoretically describe to some extent and so on, or the data in the past was not good enough to fit anything else than a radial profile to a galaxy cluster or something like that. However, given the data quality that we can expect and the amount of high-quality simulations that we have, doing something like that doesn't make any sense. Okay? What you would like to do is that kind of mapping that I described earlier. Find out yourself, or let a computer find out what is the most descriptive thing here. And if what I'm just saying right now is not convincing you, fair enough, but I will give you an example that this does not work, okay? You will not get very far with it, okay? And this is, I think, where, at least in cosmology, the big connection is right now between theoretical predictions coming from simulations and data. More data, different techniques. If you ask me which technique, deep learning. Okay, here's an example where your power spectrum will not bring you anywhere. These are the dust grain pathfinder simulations. These are simulations carried out in modified gravity models. In this case, F of R gravity models. I mean, the details do not, for the non-cosmological experts, do not matter too much here. It's a modified, gravity is modified with respect to general relativity, given a certain recipe, which is okay. That would be easily describable, for example, with a power spectrum or something like that, the differences between these models. But now you start adding massive neutrinos. Okay, we know neutrinos will have a mass, and nicely neglected in most cosmological analysis, but it's a fact that we know that neutrinos are not massless. And if you start combining these F of R gravity models with massive neutrinos, you end up with something which is actually highly observational degenerate. Okay, these models with classical techniques are virtually indistinguishable from each other, and are also partly indistinguishable between each other, and also with respect to lambda CDM. I will show you an example in a second. So this is going to be our first exercise here. We are taking basically surface mass density maps of structure formed in these 9 different models of modified gravity plus massive neutrinos in different variations. We project them onto 256 by 256 pixel maps on a scale of roughly 1 square degrees. We have them at 4 different source redshifts, so basically how deeply we probe into these different boxes. We create 15,000 maps like this per model as a training set. So this is where we tell the algorithm, this is the map, and this was the cosmology. In this case, just a number between 0 and 8. We have 9 models. So we are mapping a map like this into a classification. I'm coming from model 6, which is F of R4 with neutrino mass, yada yada. Okay? 15,000 maps per cosmology as a training set, 2,500 maps as a validation set. With validation, I mean that the network, the algorithm, doesn't know the labels, but we do. So the network is not training on these, but we check the performance on of the network along the way to basically figure out if we are on the right way, okay? Once we are happy with the validation of these 2,500 maps, trained with 15,000, we open the last box, which is the test set, and for this we were completely blind, okay? I'm honest enough, when we wrote the paper and so on, I opened those 1,500 maps the day before we submitted, okay? So it's something everybody has to do these days, okay? Otherwise, if you want to be, well, if your problem allows for it, okay? Let's be fair. But if you're doing this kind of analysis non-blind, it's no point, okay? Good. This is an image classification problem, nothing else than what, this is cat and dog problem, nothing else. And here is the observational degeneracy. These are the power spectra of these different models with respect to lambda CDM, okay? So lambda CDM would be the one line here. And as you can see, pure F of R, like this model here, has a 40% difference in the power spectrum, okay? No problem, no machine learning needed here, okay? It gets a little bit more difficult, for example, for this F6 model. Here, you're now even in the like 5% regime and so on. So it's already getting harder with the data quality that we can expect. But then you're starting to add these different neutrino masses, okay? And then you can add up with something which is virtually indistinguishable from lambda CDM, okay? The way how we try to classify these maps are threefold. First of all, we derive 99 classical features. So these are these fixed features that I described earlier, stuff that is known to be well working and so on. And yes, I'm using the word classical for something like a Minkowski functional or number counts and so on and so on. However, we use all of them. So we use all the different statistical moments. We use the percentiles, so including the median, the min and the max. We take the PDF, we take the power spectrum of these maps, we take the p counts of these maps, and we take the three Minkowski functionals, which are possible for two-dimensional maps, throw them all into a 99-element data vector and use that for classification later. We use 2,919 features from like classical computer vision stuff, so like, for example, how they're called textures and different polynomial decompositions, Zernike decompositions, and so on. There's a great tool to do that. Basically just a longer data vector with stuff that, you know, graphics people do, image processing people would use to describe these images, but still fixed. Nothing is changing along the training here. And then we use a convolutional neural network, this deep neural network, which really applies this long chain of convolutions and different operations to figure out itself what are the most describing features in that map. And then we use different classifiers, either neural network classifiers or just, you know, basically k-means, so distances in this high-dimensional parameter space. And here we go. These are the classical features with a pure distance classifier, okay? This is a hard plot, I know, but so this is the example for all the F4 models in the test set that we have, all the 1,500 that we look at. And here are what you see here is basically the prediction for the sample to belong to each of these 9 classes, okay? And basically this is a probability to belong, for the whole sample, to belong to a certain class. And yes, for F4, yes, we actually do get it right, okay? So there is the right model, which is the F4 one here, actually has the highest probability. But as you can see from the error bars of these little notches here, this is not a very clear classification, okay? If you do that on a sample by sample basis, you actually, out of these 1,500, you get actually only, I can't really read it, I think 600 right or so. So this is not a good classification, although on an ensemble basis, right, okay? But on the other hand, I mean, look at that. That was not a very hard problem, okay? And this gets worse and worse here for lambda CDM, for example. First of all, we actually would classify it wrongly as this model, and it's basically degenerate with everything, okay? So there's no clear distinction between anything. You can use a certain, you can use these computer vision features, so the slightly longer data vector, and as you can see, yeah, maybe something's better, maybe something's worse. Bottom line is this is not working, okay? You can use a better classifier, so instead of distances in this high-dimensional parameter space, no, not that high-dimensional, 99 or 2919 parameter space, and you use a neural network to map that into the classification, so in this one number at the end. There you can see, okay, now we are actually in the business, okay? And this is not surprising because the feature is there, okay? It's just this distance classifier was just not the right choice to do that, okay? Do a neural network and yes, the simple one, no problem, okay? But look at the non-simple ones. This guy here. And here we are looking in the regime, you know, all these like little cyan lines here, okay? So the simple one, no problem, but surprise, surprise, all our really observationally or classically or degenerate models, the neural network as a classifier will not change that, okay? All right. This is the convolutional neural network. Okay. Still, this is becoming a really, so here are the details. The network has 14 million parameters. And this is how it looks like. Please look at the paper if you're interested in the details of that. All our codes are public and so on, so you can use all this. Anyways, now you're in the business for most of the model, but as you can see, certain models still have a problem, okay? Still not so, still relatively hard to classify them correctly. Yeah, but we have not, so this is pure machine learning here. However, we can do a little bit more physics here. There's one thing that we have not used yet, which is, and this is something that we can do also with real observations, which is the fact that we can do tomography, okay? We will have maps at different source redshifts, okay? So let's switch on tomography. So instead of putting this 256 by 256 with one redshift channel into this neural network, let's put in 4 source redshifts. In computer vision talk, this is just adding 4 channels instead of not RGB, but now redshift 0.5, 1, 0.5, 0.5, 1, 1.5, and 2. And voila. F4 is not even on the scale anymore. So there, we actually just misclassified like 13 out of these 1500 maps. That's why that sample mean is not even, that's a 1. Okay, this is a perfect classification. Lambda CDM is basically the same, all these other methods all the same, and so on. But now we actually start also to get those really F6 models which are really degenerate just within each other, okay? Now we, at least on a sample base, maybe not on a map-by-map basis, but at least on a sample basis, we are getting them right, okay? So, of course, this is not entirely fair to all these other methods. We just use the tomography for the best method. But what you have to compare is this. This is deep learning, and you compare it to this, okay? So, you may not like deep neural networks, but the one argument that you have to deal with at some point is they work. Okay? So you have to get around this. You have to present something else that works. And at least for that problem, which is hard models, this doesn't work. This works. Do tomography and the problem is actually solved. Okay, summary of the results. Read the paper, it's accepted by now. And this is actually, Google has done that. There were a lot of images going around. So from all these images that you put into Google searches and so on. So what Google does, if you give it an image search, okay, you give it an image of a fountain which you have seen of at some trip to Turkey, and you want to know where that is, Google does this, okay? Nothing else. And they publish these kind of so-called deep dream images, basically what their neural networks are dreaming of. Because obviously these networks have some kind of internal representation of these images, okay? And Google published these, and yes, there were a lot of very like scary looking dogs, and it was really scary images. Google Deep Dream, and you will find very interesting stuff on how image searches fast with computers, okay? However, these are the main features that our network thinks are important to classify these maps. And they go from a very early stage of the network, so all the way on the left here, down to a very late stage, okay, where you have applied already a lot of these filters, okay? So at an early stage, the network thinks, let's look for blobs on a grid. Okay, that's not too surprising. It's structure formation. After all, this is the dominant channel here. I mean, we know that gravity wins in these things, right? We are looking for structure. Second step is, let's look for slightly more perturbed blobs on a grid. Next stage is, let's look for slightly elliptical blobs on a grid. And then really, really deep down into the network, let's look for stuff like vaults and look for stuff like voids. And there are some blobs in there. Keep in mind, we have 13 million parameters in this. So these are just single convolution kernels, but it's the combination of millions of them which make the decision, okay? But these are the kind of things the network is looking for, okay? And this is really just to show if Google can show you images of scary dogs in front of cathedrals, this is what mass mappers dream about, okay? Good, we use the very same technique to basically, Mario knows that I'm a cluster guy, a galaxy cluster guy, meaning I spend a lot of my life deriving masses of galaxy clusters, concentrations of galaxy clusters, from weak lensing shear catalogs, okay? Well, this is a regression problem now. What we do here is we use a semi-analytical tool from Carlo Giaccoli. It's called Mocha. It basically creates you a very, very fastly simulated galaxy cluster with a lot of observables, including galaxy shear catalogs, as a function of, the mass of the thing, the mass concentration relation that thing follows, the subhalo fraction of that thing, the BCG mass of that thing, and so on and so on. The good thing about Mocha is it's extremely fast, and extremely fast. In order to create 100,000 clusters per redshift for me, Carlo still took a weekend. That might be Carlo though, I don't know. But we basically created 500,000 realizations where we know what is the mass, what is the concentration, what is the BCG mass, what is the subhalo fraction, and so on. We use 75,000 of them. So here are examples. So this is the potential of one of these samples. This is the convergence or the surface mass density of one of these samples. And these are the two shear components of that sample, which you can use to construct something like a deep lensing galaxy catalog as you would observe it. And the idea of this test now is put those catalogs, these weak lensing catalogs, as you would observe them directly, into a neural network which is very similar to the one that I used before, and basically extract exactly what was the mass of the thing just from the catalog of shears, which are those bottom two panels here. What was the mass of the thing, what was the concentration of that thing, what was the BCG mass of that thing, what is the subhalo fraction, and so on and so on. There's triaxiality here, which is a topic I hate and love, and more hate, and will not talk about it today. Does it work? Oh, hell yeah. So these are the reconstructed masses, and you say, oh, wow, there's no bias, but there's a huge scatter. Welcome to lensing. This is a pure projection effect. You will never get better than that. Believe me, this is the theoretical scatter you expect, and there's zero bias. Full stop. Concentration, this one here. Wow. This one looks bad, right? This is BCG mass, which I actually expected a complete scatter plot. But still, you have a slight bias, a huge scatter, yes. But this is BCG mass, which means the area affected in BCG mass on these fields are probably the innermost 10 pixels of this. It's a teeny tiny area. And still, you get a good constraint on it. It's pretty amazing. This is subhalo fraction. This is just, well, it's not hard, right? Just count. And if a neural network can do something, it's counting. More to come, but this is exciting, okay? Because, again, the input would be just a sheer catalog, okay? No mass reconstruction, no photo Z selection, and so on. You can make a network learn that. Mass out, concentration out. For Euclid, treasure trove. Another thing that we do is so-called recurrent neural networks. So here, here the idea is your input is not some kind of spatially ordered data, but it's a kind of timely ordered data. It's a sequence of data. Best example or most important example of timely ordered data in the world out there is language. Okay? Letter followed by letter. I mean, that's how our language works. It's somewhat timely ordered. Okay? If you say hello, it's important that the E comes after the H. Okay? You can use that. This is now a different neural network, and I'll have not the time to go into the details of that because they are kind of tricky. But the idea is you can basically use another form of neural network, which is now less spatial, but more timely, hence recurrent. It basically knows what happened before, not next to me, spatially, to make translations, okay? This is a screenshot that I took yesterday, okay, from Google. If Google does something like this, this is what's running under the hood, okay? And it does stuff like machine learning is great. I don't know if this is a good translation, but at least you get the gist, okay? The amazing thing is you can train a neural network on English-Italian to learn English-German. It's incredible. Read some blogs that Google does on that, but it's amazing. Why is this important for cosmology? Because radio data is very important for cosmology, and radio data will always suffer from the fact that you all have mobile phones and that there are little drills, drilling holes into the wall, and that there are radio stations and so on, and you can build your telescope in the middle of Australia or in the middle of South Africa. There will still be the problem that you have so-called radio frequency interference, which is all the kind of stuff that you don't want. Here's an example of, so this is a radio signal here as a function of frequency, the so-called waterfall plot as a function of frequency, the time-ordered input of that radio signal. You want something, if you do it one slice through that waterfall plot as a function of frequency, you have a signal which looks something like that. And because, look at the frequency range, so 85, here's 90, all these little peaks here are the local radio stations, okay? In order, and this is a logarithmic scale, so on top of this tiny, tiny signal, this is actually what you can see, okay? You can use those things which translate languages to translate radio dirty signals into radio clean signals. And as long as you know how your dirty signal looks like, this we perfectly know because we have it around it all the time, and you can simulate how your clean signal would look like. And you apply neural networks, blah, 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 and in the end, this is the signal. This is the blue line is the, this is the observed signal. The blue line is the real signal that you would expect. No, the black line is that, and the blue line, which you can barely see, which is good because it's right on top of the black line, is what the neural network makes out of that red mess, filtering the signal and getting basically exactly the right answer. I mean, it's pretty bad at this mess at the outskirts here, but nobody cares. The actual signal that we're interested in is this one. Bottom line is, same thing that Google uses to make my life in Italy easier, makes the life of cosmologists easier, denoising these signals. Final application. Who has seen these celebrities? Any guesses who they are? Well, good, they don't exist. They're computer generated. okay? They are generated from samples like this. So this guy I know, I think he's in Masters of None. This guy I somewhat know. Looks a little bit like Angelina Jolie, but it's not. So anyway, these guys are real. NVIDIA, my proud sponsor, used a large database of this to create guys like this. They're completely made up, okay? They're not real, okay? And you can see mistakes. I mean, his eyes look a little funky, right? Or what else? I don't know. I don't think her hair fits her face, but anyways. But even the background, right? I mean, there's like even... I mean, the network doesn't care if this is background with, I guess that's Huawei, the Chinese telecom guy. The network doesn't care if it's a face or a background. It will even get the background realistic, okay? And what's happening here? This is a so-called generative adversarial network. So this is now two neural networks fighting against each other. One of them is a generator. The input of the generator is white noise. You feed that network noise, and it gets something out. Then there's a training set. So real images of people, okay? And the generator creates a fake image, okay? It will not be very good in the beginning because it doesn't know what to do, right? You put white noise in, you have some randomly assigned parameters, you will get white noise out, okay? But then you have the real images coming in from this side, you have the fake images from the generator coming in, and then you use another neural network, the so-called discriminator, and ask one question. Is that a real image or is that a fake image? And you tell it the answer in the end, okay? And then you optimize that in the same way that I described earlier. So what's going to happen? The first thing that's going to happen is that the discriminator has a really simple life in the beginning, because this thing is just generating white noise. Those guys obviously have very little entropy in them, right? So those will be distinguished in an instant, okay? But you're also optimizing another thing. You're optimizing the generator, okay? In other words, you're asking the generator start being better at fooling the discriminator, okay? And this is a balance, a tricky balance. But in the end, you can use that to use training sets like that to create out of white noise something like that, which is in fact so realistic that A, you would think they're real, and B, even a neural network would think they're real, okay? Why is this important for a cosmologist? I'm a weak lensing guy. That means I do a lot of image simulations, a lot of weak lensing image simulations. If you want to do a perfect image, as good as possible image simulation, what kind of data would you use if it's real? Well, Hubble Ultra Deep Field, for example. What's the problem with the Hubble Ultra Deep Field? Well, there are only 9,000 galaxies in that. Well, if we can create phases out of that, then yeah, we can create galaxies out of the Hubble Ultra Deep Field, okay? This is not perfect, okay, this is work in progress, but the idea is absolutely valid, because if people can do this, we can do this, if I find the time. In other words, those galaxy images would be so realistic that for sure you can't tell the difference. Here you probably can tell the difference. But even a neural network cannot, and now you can use billions of galaxies to build image simulations for Euclid, for example, and so on. Our code is all there. Cons about networks, sometimes it's hard to understand what they really do. Fair enough, but there are ways around that. Lots of pros. Enormous flexibility, can be used for a lot. And, well, here I use black box and open box models. If you use their deep neural networks the wrong way, they're really just a black box for you. They're really just doing a task for you. But you can do stuff like that. You can open this box and really look like, obviously this network is doing such an amazing task discriminating these maps. So maybe we can learn from this network what is actually important, right? So maybe we can actually use that. We cannot, optimize, at least for this problem, we cannot optimize 14 million parameters. We cannot look at 14 million parameters models at the same time. The network can. That's good, because it runs on GPUs and so on. So maybe we can harvest that and actually get some more physical understanding out of this, okay? This is why I wrote here, it can be a con if you use them in the wrong way, but it's also a pro because you can learn a lot. You just need to invest some time. And believe me, understanding a 100 million parameter model is a task for itself. And that's it. Thank you.
I hope you have questions.
Probably silly question. What would happen if you took the faces and you would make them out of focus?
Oh.
Blur them, or
No, I mean so it's a good point. One of the first con that I write here, right, is you learn what you train with. Okay, so if you train on out of focus images, you would learn out of focus images.
Yeah.
So, in other words, if you put non-crisp images in there, the network doesn't know what an image is, right? It doesn't. It will literally just find the best description for supervised learning, right? It will find the best description for what you put in. There is no way of fixing something because a network doesn't know what a focus is, right? So the answer would be if you put this kind of network would the answer is it would not be able to create out of focus images. Or if you put out of focus images into as a training set, then you would have a network which will produce perfect out of focus images.
Yeah. My reason of the question is, okay, I understand that if you're using simulations, you get wonderful results. But the question is, what happens when you use real data which have a lot of measurement errors and so on and so on?
This is why I love machine learning and hate cosmology, right? Because from a machine learning perspective, this is not a valid question because your training set is something you start with. And it's implicit that if you use this kind of technique to learn from a training set something about cosmology, which is real observations, then it's implicit that that training set is a valid representation of the input data that you're using. Making that implicit assumption a reality is a huge task.
Yeah, but this is what is, I don't understand.
Yeah, but we have to do it.
What is the consequence of this? I mean,
Oh, we don't know yet, and we have to figure. I'm not saying this is going to solve all cosmological problems tomorrow. The main task for making this work, for example, oh, by the way, this kind of stuff you can really start thinking about Euclid CCD image in, cosmological parameter out. In other words, all the stuff, learn that it's important what galaxy shapes look like and so on. Learn that it's important what redshift distributions are and so on and so on. So anyway, so this is some crazy idea. In order to make that work for cosmology, this needs to be figured out. I'm not saying anyone is at the stage which is necessary or the level which is important. But to be honest, this kind of route is just so promising that we should put a lot more people on doing that. Because free industry is doing these kind of things. They are way ahead of us, right? Cosmology is really, having its little sleep there. What's done in the free world out there right now on similarly hard problems has way overtaken us by now, and I think it's time for us to wake up. It's important to do all this. We need people to do it. I'm not saying I've done it.
Like all of you, I experience every day, many times a day, the wonders of artificial intelligence and machine learning. Each time I ask Google something, and in a nanosecond I get the whole vector of answers.
Yeah.
Yet in my work in research in astrophysics, I have still to bump into a result obtained, say something exciting, an exciting result obtained with machine learning. Why there is this gap between the huge power that has been in Google and in other similar activities, and yet in research, in astrophysics, I mean, or cosmology, I have not experienced yet a major achievement.
Two answers to that, very different answers. The one answer is the exciting results in physics, many of them is some kind of discovery, right? Those things will not discover anything by definition, because you make them learn something you already know. Okay, first answer. Second answer is, what I'm advocating here is that you should use these kind of techniques for data analysis, right? And that's when Mario comes into play. In principle, on paper, a neural network should give you a much better precision and potentially also accuracy on, for example, deriving a cosmological parameter, okay? So for example, some kind of data set, even some combination of Planck and V-cleansing and so on, which gives you an accuracy on some kind of parameters to some great precision, blah, blah, blah. If you consider that it's exciting, I don't, but okay. Then that would be a great result. The reason why this is not happening is the discussion that we had before, because all these little steps need to be done. And there are not many like me in cosmology right now. So the manpower working on this is rather simple, and I really have no idea why. Maybe because of the first answer. This is not exciting. It's not. You're just teaching you're literally teaching a machine something you already know. The real work, the real cosmology work, would have been done by the simulators, because that's the model you're trying to constrain. There's no discovery. So maybe they're connected. And in the free industry, the problems are just different, right? I mean, it's really just about data. If you harvest enough data, it can tell you probably a lot about you. And those are the exciting things, right? We think that's exciting, it's probably scary. But yeah, I hope that more or less answers that.
Just to recap Fabio's question, my experience on photometric redshift, I can tell you from my experience of photometric redshift, I can tell you that on photo Z, the neural network are not going much better than classical photo Z.
To be honest, you know, I'm a lensing, even shape guy, and so on and so on. To be honest, when I talk about photo Z's, I was just dancing.
Okay, but a lot of people work on photo Z, and they are not getting a result much better than.
No. I mean, I tend to give very excited talks. You know, I'm not claiming that this is the solution to everything. But at least I hope that I convinced you that the 4 problems that I've shown you today, they are pretty good solutions for that. Photo Z's, maybe they should have better people work on that done, which do the neural network part. No, fair enough.
Speaking with people working on neural network, they told me that when you have a good catalog, either a neural network or a classical photo Z gives a good result. The problem.
No, that's a fair enough point. And again, I really don't try to sell these things as the solution to everything. If the task was, just to give you a very naive example here, if the task was to distinguish, where is this curve here from this curve there. So if the information is there, why would you use a neural network? So as you say, if the catalog's good enough, you probably get similar results. No, wait. But what I'm claiming is that if you're trying to distinguish these maps, then the neural network works. And that's what I have worked on. I've not worked on photos.
Yes, but you don't put the noise on that map.
Oh, no, I'm not showing noise here. No, but we are putting noise on these maps, of course.
Only show noise.
Yeah. But again, we can. No, fair enough. No, I appreciate but I genuinely believe that these things will be very useful for many things.
What about the dependency of the architecture of your network?
Almost insignificant. As long as the network's deep enough.
So you can change the.
You can change the so-called hyperparameters. As long as the complexity of the network is deep enough, it doesn't matter. 3x3 convolutions, 5x5, whatever. You're combining tens of millions of them. It doesn't matter.
Small question. In the representation of the inner layers,
Yeah.
after the solution layer, you have an image with more than 3 channels.
Yeah.
So when you show what the neural network is dreaming, you have grayscale images.
Yeah, these
How do you choose?
you choose those layers. So this is one channel. Okay, this is
how
one.
do you choose
The ones which give the largest response to white noise.
Okay.
So the ones, it's a very specific technique. You feed white noise into that, and then you do not do a gradient descent, but a gradient ascent to basically maximize the response of the network to a certain image, and that image is your answer. And those are just those layers and those channels which gave the strongest response.
Okay.
However, the real classification or representation is done by the combination of all of them. But those are, if you want, the most important ones. But again, there are 4 of them shown here, and there are millions in the network. So even if this is the most important one, leave it out and you will not lose anything. It's just, they're so deep that they're A, hard to understand, but also incredibly powerful.
Questions? So I'll chime in a little. I understand that the big challenge for a project like this, which is ultimately, ideally we would like to have data in, science out.
Raw data in, cosmological parameter out.
And the big challenge is what you train on.
Yeah.
Because the people who do cat, dog classification
easy.
have a limited amount of latent images because humans are good at telling cat from dog without knowing how we can do it, right? So in your case and also in our case, the problem is how you generate the training data, right?
Not even in the physics case, also the free industry has the same problem. Creating the challenge here for any application with these kind of methods is not the method itself, it's the training set. The training set needs A, to be big enough, and B, realistic. So if your raw data in is really, for example, a CCD image or a real-time radio stream or whatever, as long as you do supervised learning, in principle, your training set must be of the same quality. It must have the same features and the same systematics and the same, little glitch in that chip on that board of that CCD imager, okay? And it's unclear how important those things are. And as I try to answer, this is the big challenge. A, to make enough of these simulations and make them good enough. So ultimately, I think we are not going to be limited by these techniques, by the method, but we are going to be limited what we can teach them. Because obviously, if you can create the perfect simulation of the universe, then you don't need to do the task by first principles. You need to find out what is the balance between our not knowing and still getting at least an unbiased result. I don't know how well. These problems are obviously very limited, but these crazy ideas like, raw data in, cosmological model out, I think they will ultimately fail on what I just described.
So, for example, take the Planck database and the chosen parameters they got out of it. They did without.
Yeah. But also because...
So, suppose you want to apply machine learning again to the same data.
Yeah. I mean, people do that and they do get similar results, right? Planck is probably, the thing is, Planck is probably not the best example here because I tried to motivate it a little bit here. For Planck data, using machine learning is unnecessary because, it's I'm not saying the Planck data analysis is easy in any sense, but at least it's the linear regime. We think we understand most of our systematics and so on. We know, how that power spectrum, or how that TT or that polarization power spectrum relates to our cosmological model and so on. Using something like what I described earlier is probably A, not necessary, and B, introduces that danger of that you're not really understanding what you're doing. Because especially in the Planck pipeline, you understand up to the crazy level what you're doing, right? Statistically and also systematically, hopefully, right? But my motivation for that is for nonlinear stuff. This kind of, what do the binary do? We know that the power spectrum is failing on nonlinear scales and so on. So there we just need more clever descriptors of our data. And there machine learning becomes interesting. For Planck, it's shooting with something which is very big and you don't fully understand on something relatively simple, and that can create havoc. I'm just saying for some problems we may have to.
Thank Julian again.
What do you mean? Oh, no. I'm not a very...
Sorry.
Hey.
Just a question. Have you tried to...
Sorry, by the way, I didn't want to give you a snappy answer.
No, don't worry. Don't worry.
Yeah.
Just a question. Have you tried to apply your network on detection of image? For example, if you have a galaxy,
No, so I don't. It's one of the things that, so as I said, I'm a little bit in this galaxy image business because of these image simulations. And a lot of people in Bologna are interested in, a person, I work with Henk Hoekstra in Leiden, he's interested in these kind of things. Personally, I have not done it yet. It's something we have already thought about, that's for sure. What we have done, for example, we have used these neural networks for actual shear measurement, and so on. So this is something we have done. There's just the usual thing, it depends what you're training on. No, it's very interesting. I personally, my list is so freaking long. And so the one thing where I get closer to the data are these actual image simulations. So that's my one thing where I actually try and produce some CCD data. Besides that, my personal interest is a little bit more abstract, like simulations and what is dark matter distributions and so on. And so on. It is kind of on the long list. So. Anyway, if you're more interested in that, just shoot me an email and we can. No, because we have the hardware and we have the software knowledge. I'm quite so I would be more than happy to get something.
Sì, è passato anche anno.
These slides are public or?
I will make them. They will be on my website.
Because I have the defense of my thesis in 1 month.
Yeah.
And I want to steal some of your ideas.
Oh yeah.
To present in a very quick way. Deep learning. Because I have 10 years.
Yeah.
Yeah,
don't worry. Either I can send you my talk right away today, maybe after lunch, or I put all my talks on my website at some point.
Because I found it
Yeah, no, don't.
concise and.
No, my first talks on deep learning did not look good.
Yeah, because I found it difficult.
Because it's difficult to introduce these things.
Yeah, it's like the concept itself. In the end, it's very easy.
It's very easy, but it's very abstract to describe the process. No, I know. I've given a lot of talks where this was not that smooth.
Thanks for this overview.
Thank you very much.
Possiamo mettere quella cosa della presentazione. Sai che avevo ancora provato a farla?
Yeah. No, that's what I meant when I said, like, if you can create a perfect simulation of the universe, you don't need to look at data.
Ah, però questi spunti anche su come presentare proprio.
Se vuoi venire a pranzo anche con noi, oppure se no dopo, perché lui starà con noi fino alle 4:30. L'ufficio nostro. Quindi sì.
So the problem is there's no creativity, right? You're really just learning a simulation. That's what you're doing. So a neural net, that's because people call it AI, right? Artificial. There's no intelligence here.
Devi pensare alle cose
è il punto finale
e lì infatti sarebbe bello chiedergli, magari lui ha avuto delle altre idee
and to understand them. So you really need to know when you're actually biasing your result
quello anche sarebbe carino,
because you have overlooked like one thing, which for some reason has the same, leaving out that thing has the same signature as some feature that you're trying to find.
Magari lui ha qualche altra idea.
No, I mean the biggest limitation of this
penso che più ci teniamo in
learning the right thing.
Magari anche
si dovrebbe anche fare se le faccio quello ha un discriminatore.
So, well, I already introduced you.
Okay.
And then let's go for lunch. I mean, you can drop your backpack in my office, which is also Alessandro's.
I think we'll pass in the office in the afternoon.
Yeah.
So.
I think you know so much content for us. Okay, we can leave it there. Okay, so
see you later.
See you later after lunch.
Yeah. So close to my daughter. There's a really cute baby snoring.